রৌনক, কি শরীর ঠিক আছে? নিচে? আচ্ছা, আচ্ছা। ঠিক আছে।
Good evening to all of you. We are at the fifth day of 1 week faculty development program on research methodology and data analysis. And today we have two eminent resource persons, Dr. Shomo Saha and Professor Bidyut Das, to talk on different aspects of data analysis. I request Lopamudra Bhattacharjee Madam to introduce resource person for the first technical session and to take charge of today's session. Madam, please.
Thank you, sir. Am I audible?
Yes, very much. Yes.
Okay, thank you. I would like to wish a very good evening to all the respected professors, my colleagues, and all students who are gathered here for this workshop. Now, I would like to introduce our first resource person, Dr. Shoma Shaha. Dr. Shoma Shaha is an assistant professor in commerce at Vivekananda Mission Mahavidyalaya, Holdia, Purbu Mednipur. He's also associated with the Department of Commerce, University of Calcutta as a guest faculty. Before that, he was associated with the Postgraduate Department of Commerce, St. Xavier's College, Kolkata, an autonomous institution under University of Calcutta. He has earned his PhD from the University of Calcutta. He also completed his postgraduate degree in commerce from the same university. In addition to that, he has also earned his Master of Business Administration and MPhil in Management degree. He has over 17 years of experience in teaching. He has many research papers to his credit and presented numerous research papers at various national and international conferences. So I would like to hand over the session to Shomo sir. Over to you, sir. Shomo sir is there, I think.
Yeah, ma'am. Thank you for the
Okay.
nice introduction. I hope I am audible to all of you.
Yes, sir, you're audible.
Just pardon me because my throat is cracked and my voice is not okay. So, still, as I promised to take the session, sorry for this interruption or sorry for this problem, whatever I have in my throat. So, please bear with me. I hope I am audible to all of you.
Yes, sir, you're audible.
So, just is my screen visible, madam?
Yes,
And
sir. Yes, sir, your screen is visible.
okay, just so I hope the PPT is now visible to all of you.
Yes, sir.
Yeah, thank you. So formally, we begin the session. I definitely thank the KBSAA organization along with the Nowgong College, Assam, Jhargram Raj College, Jhargram and Domkal Girls College, Murshidabad authorities to allow me to be a resource person in this session. I don't believe that I'm a resource person. So still in the field of research and in the field of accounts and finance, I believe that I'm a student of that. So we all are student in the field of research. Whoever is the participant over here. So based on that, today we are in a platform to share certain views. And my humble submission in front of you that definitely we are going to share something about regression. Majority of us from our graduation day we are knowing the regression. So here the basic objective is the regression. There is a basic two types of regressions are there, as we know, that's a bivariate and multivariate regressions are there. So how we will run it in a statistical software package that's widely used, that SPSS. So we are going to learn it together, or you just share our views how we'll run that SPSS bivariate and multivariate in uh, SPSS. That's a basic, the bivariate one and the multivariate one. As we know, what is the bivariate? Bivariate means where the two variables are there. Means the independent and one dependent variable is there. That's a bivariate case. And multivariate, we all know, where we are regressing for more than one independent variable. That's a multivariate case of regression. So we'll start with the basics of regression analysis. As we know, the regression of whatever we are doing, actually these are the linear regression. So as we are if we start with the regression, then the pre-step of regression should be correlation, which Professor Shahar dealt with yesterday's class, and Dr. Sudhi Dhor sir is also dealt with that normality test in the last session with you all. So that's a basic prelude of regression analysis. So without, if there exists no correlation between two variable, we all know that we cannot run a regression analysis. And the correlation also, by definition, it's a linear association between the regression as well as whatever the regression bivariate and multivariate, usually normal optimum least square regression we are using, that's basically a linear regression. Now, the pre-step is, I already mentioned that it's a correlation. So if the correlation between two variable are significantly correlated, or if even if it's a positive or negative, doesn't matter, but the correlation should be significant enough. Uh, Based on that, we can go for a association. So try to find it out, the association between the two variable. That basically we go for a linear regression. So if I just go by the definition of linear regression, generally it is used when to predict the value of one variable based on the value of another variable. So we know one variable and you want to predict the value of another variable. That's why you are going to use a linear regression. Now, in a bivariate case, we have two variables. One is supposed to be a dependent variable. Sometimes it's known as an outcome variable. And there is also the another variable, which is an independent variable and sometimes called the predictor variable. So we have two variables. One is a dependent variable. Another one is an independent variable. Now, this is a simple example to cite the linear relationship or linear regression cases. The first one you can cite whether exam performance can be predicted based on revision time. Something like this whether cigarette consumption can be predicted based on the smoking duration and so forth. Now, in the first case, whether the exam performance can be predicted based on the revision time. So here revision time will be your independent variable and the exam performances is your dependent variable. So in that way, you have to identify the basic dependency relationship with the independent variable. The simple example, you can also cite the rainfall and the paddy production. We know that the paddy production depends on the rainfall. So paddy production in units definitely comes under the dependent variable and the rainfalls comes under the independent variable. And we try to predict the value of the paddy production if the rainfalls increase or decrease in certain portion of a country or a state, something like this. If you don't have two or more independent one, you need to use a multiple regression. So that's already mentioned that if my independent variables are only one, then we have to go for a bivariate regression. And if our independent variable increases from one, then we have to go for a multiple regression. Now, these are the most important part of it. And we're going to spend more time on these assumptions because sometimes what we find in my research area, we fail to follow the assumptions of the regression and we just run. Say generally from the student perspective, when you start with the project in student level, then definitely they are inclined to use the SPSS or any software tools and try to have the results. Now, basically, research is something, these tools, whatever the packages now we are having with us and which made our life so much easier, these actually help us to get the results. But this is only a tool which can help us to get the result in a simpler way or not in a hazardous way. But the research starts from once you get that results. So your task as a researcher or as a PhD scholar to go for analyzing the data and the results whatever these softwares are providing to you. Our task is to interpret and relate it with the objectives. That's the basic objective which I usually started, that my objective, say for if I go for a tour plan, simple way, not for a big PhDs, if I want to go for a tour plan, I want to go to Kanyakumari, and what happened, my results are saying that I went to Himalaya. So generally this happens for the student cases. So the results are not aligned with the objectives. Our research basic focus that we have to align our objective with the results or the interpretation of our results. Now for that, these assumptions of each and every model, whatever you are going to apply in your research, because when we are doing the sums in a statistics class, these assumptions we never checked. But when you are a researcher in a research paper or article, or if you are going for a PhD thesis, then definitely this assumption need to be checked. Without validating this assumption, if you run a model, the results are simply spurious, and the coefficient values, whatever you are going to get, actually says nothing. So we'll start with the bivariate case assumption of regression. So assumptions are very important in our case. Now generally two variables should be measured at a continuous level. They are either interval or ratio variable. So generally the scale variable, the previous speakers last day has talked about this ratio scale, the interval scale. These are the continuous level data, and we also have a discrete level of data in nominal and ordinal scale. So generally in regression, we generally try to follows in normal bivariate cases the continuous level scales, interval or ratio variable. The question is, yeah, you can run a regression on the ordinal and nominal variable too, but usually we follow a continuous levels regression. Now there needs to be a linear relationship between the two variables. If there is no linear relationship, the regression cannot be stated as a linear. It should be a non-linear regression. The total methodology differs. So prior to begin with a regression, you need to check whether the two variable in your case you are taking for a regression analysis should be linear or they hold a linear relationship. Now the next one, your data needs to show homoscedasticity. I hope these are the two terminology you already come across in terms of research, homoscedasticity and the heteroscedasticity. Generally the higher order moments, or you can say the variance, generally if it's a homoscedastic, it means the variance of the residual term of the regression is actually constant. And a heteroscedastic means the residual of the regression, whatever the variable regression residual we are getting after running a regression, that residual part or the error term of the regression equation is the variance is not constant. The variance is actually varies frequently along with the scatter diagram or along with the linear line. So that's in simple way we can say that this is homoscedasticity, where the variance of the residual is constant. And if the variance of the residual is not constant and it varies frequently, for a time series data with time, for a cross-sectional data with time also. So in every sphere, every set, the variable should be variance should be constant. And if the variance is not constant, then the data set is supposed to be not homoscedastic. It means it's a heteroscedastic. So you whatever the data or the variable you are choosing, actually for a regression analysis, you need to test it for the homoscedasticity. If it's not homoscedastic, and if you run a regression on a heteroscedastic data, generally the coefficients whatever you are having actually doesn't make any sense, or the generally the coefficient values are usually less. The probability values also coming very less, and that's why the interpretation what exactly you are try to get out of the coefficient value of a regression, generally if the variables are heteroscedastic, then usually the results, how we are going to interpret it, it actually gives us nothing. So that's why this part has to be checked prior to go for the regression analysis for bivariate case. The residual errors of the regression line are approximately normally distributed. So the first one you have to check for the residual homoscedasticity, and the second one you have to go for the normality of the error term or the residual term. So whatever the residuals we are having from a regression line or regression equation, then definitely you have to check for the normality of the residuals. Again, that optimum least square, actually what we are assuming that the error terms are normally distributed with a standardized mean. In a standard normal distribution, mean 0 and standard deviation 1. That's a standard normal. Accordingly, we are actually assuming that the residuals of a regression, the error term or the residuals of a regression line is actually approximately normally distributed. If it's not true, then definitely the model, whatever you fitted for the regression, actually gives you nothing. So that two for the residuals and the first two for the variable you have to check. So the first two is for the variables, the continuous or interval or ratio level, and linearity of the two variables. These first 2 points definitely depict the variable assumption, and the last two of this slide is basically the residual assumption. So these four assumption has to be checked, needed to be checked prior to run the regression. The first two and the second two after running a regression, the homoscedasticity test and the residual test. Now I already shared with Lama sir I know that this you are all sat with the SPSS, and our task basically today to run that SPSS with you all together. So that's why I already send you or shared this data set in .sav file with you, and also send you the 14 days link of SPSS. I hope all of you are sat with the SPSS in your laptop and the data set open. So we are going to use this exam revision.sav data. Now here four variables are there. If you just look at the data set, if you have just if you just look, I hope the SPSS window is visible to you. If you have the data set with you, then definitely we have four variables in the data set. First one is a score, second one is a hours, third one is a anxiety, and fourth one is a point scale. If I go to the variable view, it's simply written in the levels. That first one is exam score, second one is hours spent on revising, third is anxiety, and fourth one is a level entry point, so previous marks examination. So these are and all these are scale data. That's a continuous level data. This is written over there. So these are the four variables are there, and we try to run a regression on it. So our task is over here based on that variable. So to check whether there is a relationship between exam score and revision time. The data whatever we are using here is a cross-sectional data. So to check whether there is a relationship between exam scores and revision time. Now the independent variable is a revision time over here, and the dependent variable in our case is an exam score. Now there are certain syntaxes are there, or in SPSS we need not to write the syntaxes. Generally the drop down menu make our life much easier, which is not so easier in R. What exactly the free, but these softwares have cost. So generally now it's a tendency that we are moving towards the R. The next session we have with us a resource person who will give you the knowledge in R and how to run all these tools in R. Now generally these are the steps is there in the PPT. I'll definitely share the PPT with you so that it can help you. Now with SPSS, if I have to run it, so to run it, the steps are you have to go to analyze, then we have to go to regression and the linear. That's a step. So in this window, in the data view, we have to go to analyze, then we have to go to regression, and in regression we have to select the linear one. Now in this linear we have to select the dependent and independent variable, so it's a bivariate one. Our exam score is a dependent variable, and the hours spent on revising we took as an independent variable. So this is a simple one. If I just go to the statistics, generally this estimates the model fits is already checked, so just go for it, continue. Plots, if I need a plots, then definitely we have to go for the plots. This is, you can check that the standardized residual plots they are going to make. If I want to go for unstandardized, so I don't require the standardized residual plots. This is the saved data are there. Right now we are not requiring for a bivariate regression, or if you want to go for this homoscedastic and the normality test of the residual, then for that you have to check this. So what exactly we are going to do is basically we have to save the data. Now save the data for the unstandardized and standardized for predicted values, and residual standardized and unstandardized for this one. And in a prediction interval, generally you have to take it that mean value actually. So we are running the model on the prediction intervals on mean basis. So these four in a predicted value column, you have to check this unstandardized and standardized residual predicted values, and in residual unstandardized and standardized you have to check it. And for a model, basically prediction interval, which model you actually fit, you have to fit a model with a mean. That's why you have to select that mean, then just click on continue. In options we have nothing to do. Bootstrap also we are not using, and simply if we click OK, we'll get the results. So to revise once more, that the steps that we have to go to analyze, then we have to go to regression, then linear, then we have to select the dependent variable, which is exam score in our case, and hour spent on revising is an independent variable. So first we have to select the variables, then we have to go to the statistics. Here we have to go for a model fit and estimates. Others are actually not required right now. So we go for continue. Plots we are not requiring right now. We have to save data because we need to check the homoscedasticity. So for that, and the normality of the residual. So that's why predicted values, standardized, unstandardized, and residual standardized, unstandardized has to be checked. And for prediction intervals, the mean has to be checked, and then continue. And now your task is just click on OK, and you will have the results with you. So these are the results we are having with us. So this is a model summary. Then we have the ANOVA table. Then we have the coefficient table. And the residual statistics are there. We are not going to interpret that only. Now I hope all of you know how to interpret. So actually we are moving to the interpretation part more, that how to interpret, because these are the few steps this gives you. So even if the variable are not normal, variable are homoscedastic, SPSS cannot understand whether the variable is normal or homoscedastic. You have to understand through the results of it. And whatever the garbage you will put in this SPSS, the garbage will give you some results. So we are, in simple words, we are saying that is garbage in and garbage out. So just any data you will put in the any data you put in the spaces, it will give you some sort of results. Now whether these results have actually a true meaning or not, for that you as a researcher has a role to play. So how to interpret data following the assumptions. Now R value, you all know what is that R value. Just switch to the PPT part if I have the results with me. So your R values are there. So this is the results. I just copy and paste it in a results over in the window. So R value is 0.821. So that's a correlation value. R square value generally is 0.674 R square. There is a name of R square. There's a good name, like we have a nickname. So nickname is R square, and a good name of R square is, we know, coefficient of determination. And this is a model fit, and this is actually, so know how maximum of us know how to interpret the R square. So R square means here 67.4% of the variation of the dependent variable will be explained by the independent variable. So that's a simple and shortcut interpretation of R square. So the value of R represents the simple correlation, and the R square value indicates how much of the total variation of the dependent variable, that is exam score in our case, can be explained by the independent variable, which is revision time in our case. Generally, in this case, the 67.4% can be explained, which is quite large. Generally, if we more tends to this R square value stands between 0 to 1. So if you reach more towards 1, your prediction of predictability power of the independent variable is higher enough, and we always try to achieve that. So if our R square values in a thumb rule, if it's more than 5, it's okay. But what I can say, for a primary data, we are happy with more than 5 usually. And but if it's a secondary data, more standardized one, then R square should be at least more than 8. So then the model, you can say that the predictability power of your model is good, or the variable, the independent variable, can predict your model good. The next one is the adjusted R square, which is not required actually for a bivariate regression. It has some interpretation for a multivariate regression analysis, but for bivariate regression, the adjusted R square value has no interpretation, but definitely it has an interpretation for the multivariate case. We are going to discuss it in the multivariate case. Now the ANOVA table is there, and for ANOVA table, we have the F values is there, that is 37.255, and the significance level, that's a probability value at 5% or 1% level of significance is coming tends to 0. And we know at 5% level of significance or 95% confidence interval, if p value is greater than 0.05, the null hypothesis is usually been accepted, and if the p value is less than 0.05, the null hypothesis is rejected. That's a basic thumb rule. That probability value is, by definition, we say what is the probability or chance of the null hypothesis being accepted. That's a simple interpretation of the probability values. Now the software, they are giving the probability value, but when usually we do in hands, we are accept or reject or a decision, or whether the coefficient is statistically significant based on the confidence interval level. But usually in softwares, the probability value we are using to accept or reject a null hypothesis. Now here the this coefficient value actually is this significant. Now what does that mean? It indicates that the statistical significance of the regression model that was run or fitted over here is actually a good fit model. So this ANOVA table help us to identify whether the regression model we fitted is actually a good fit or not. So here, if the probability value as it tends to 0, so we say that the model is a good fit model. The model is a good fit model. Clear? So that's a simple interpretation. So repeat once more, this ANOVA table, F value and the significant value, these two value we have to look into, and if the probability value is tends to 0, less than 0.05, we say that the ANOVA value, F value, is statistically significant, and interpretation of that in regression model, whether a model is a best fit or a good fit model, this will signifies that if the null hypothesis is rejected, here it is rejected, so we are saying that the model is a best fit or a good fit model. That's a simple interpretation of the ANOVA table. And the coefficients, generally we have two variables. So we know that the equation we written like this: y equals to alpha plus beta x into epsilon, or e actually, that's a error term. But normally we are assuming that the error term is 0. there is no error left, so that's why the regression equation comes like this. Now we have to, this is the intercept from, that's a constant alpha, and this is our independent variable, our spent revising, and we have two different coefficients are there. One is a unstandardized coefficient, one is a standardized coefficient. So for our standardized coefficient, we usually don't have the constant coefficient. That constant coefficient is same for the standardized and unstandardized model, but we have the standardized and unstandardized coefficients. Spaces usually gives us the two different coefficient. So generally, if I use the unstandardized coefficients, then we have to check for the t statistics and the significance level. So we have to check whether this coefficient value of x variable or independent variable, which is revision time in our case, is actually statistically significant or not. So whatever the results actually in statistics we are getting, we actually test it for the significance of that test, so whether it's a statistically significant value or not. So for regression also, you have to test the coefficients and try to find out whether the coefficients, both the constant, that alpha and the beta, are actually statistically significant or not. Now here in this case, in both cases, for the constant also, that's alpha value, and the independent value, which is revision time over here, for both the cases, the p values are actually less than 0.05. So we are rejecting the null hypothesis and accepting the null hypothesis, sorry, accepting the alternative hypothesis, or you can simply say that the coefficients are statistically significant. If the coefficients are not statistically significant, you cannot report or interpret that results. Your coefficient must be statistically significant. So here in both the cases, for a constant value and the hours spent on revising the independent value, are having the statistically significant coefficient. So we write the equation, exam score equals to 22.16 plus 0.992 revision time. So y equals to alpha plus beta x. That's a format. Now I have a simple question in front of you. When should I use unstandardized coefficients and when should I use standardized coefficients? Now unstandardized coefficients usually actually we are using for us data which is collected through different scales. So if the scales are different, then definitely you are going to use the original scales, or you can say that original scale. So different scale, original scale, the scale you fitted, and based on that you are actually we don't say that it's a different scale. If you are selecting the unstandardized coefficient, the data, if you have to look if the scales are original, in which scale the variables are actually collected. If you are using a regression on that, then usually we are using the unstandardized one. And if you go for a standardized one, then generally here only we have to make it standardized. So that's why you are collected, your data scales are different. Say 3 variables are there and 3 variables collected in 3 different scales. If 3 different scales are there, to uniform the analyzing the coefficient value, we need to standardize the coefficients. So if the scale is same for all variable, we generally use the unstandardized coefficient. But if the scale of the data you collected upon which you are running the regression is the scale are different, then it is better to use the standardized coefficient. Now in standardized coefficient or in unstandardized coefficient, how will interpret the results? So if I took the unstandardized coefficient, and if I want to interpret that result, we usually interpret in this way, that a change of 1 unit of the independent variable x is associated with a change of beta units of the outcome of y. That's a simple way. I repeat, a change of 1 unit of the independent variable x is associated with a change of beta unit of the outcome y variable. Now, if the same interpretation we have to go for a standardized coefficient, it comes like this. A change of 1 standard deviation in x is associated with a change of beta standard deviation in y. So here we are not 1 unit, we are measuring the variance, the standard deviation. So if there is a 1 standard deviation change in the x, what is the standard deviation change in the y? So that's a simple difference in interpretation of the unstandardized and standardized coefficients. Now we're moving to the next part. 1 hour is very small actually to go for a regression in detail. Then again, in a nutshell, if I give you some sort of ideas, then definitely it will be of a good use for you. So the multiple regression is an extension of the simple linear regression. It is used when you want to predict the value of a variable based on the value of two or more other variables. You could use the multiple regression to understand whether exam performance can be predicted based on the revision time, test score, and anxiety. So here we are using all the three variables. Now these are the assumptions you need to check. Now for this multivariate one, and this assumption is a must case. Now this dependent variable should be measured on a continuous scale. Second one, the two or more independent variables which can be either continuous, that is interval or ratio variable, or categorical also, that's ordinal and nominal. That's why I said in the case that your variable may be, in your independent variable may be continuous or maybe not continuous, the discrete collected in a scale ordinal or nominal. Now there needs to be a linear relationship between two variables. Your data needs to show the homoscedasticity, and the residual errors should be approximately normally distributed. And you learned about or heard about the term multicollinearity in the last day's session. I hope all of you know also. So recall that if the independent variable is have a high significant correlation amongst each other, then the results or the coefficients of a regression, whatever we are going to receive, is actually means nothing. So that's why if there is a multicollinearity in the independent variable, how to deal with it, we need to know all these things. Now, to give you answer, in the last class also, sir talked about VIF value, variation inflation factor, and sir already mentioned that the variation inflation factor in research generally sir told 3 is a benchmark, that if the data variable inflation factor of an independent variable is more than 3, generally it means that there is a multicollinearity. I will reduce it to 2 more rigid case, that usually in higher order research generally we take it into 2, and if it's more than 2 only, then definitely we say that there exists some sort of multicollinearity and we cannot run a regression on this case. So 3 is okay, happy. Some research paper also take it's more than 10, but for more rigidity we can take it as 2 or 3, whatever you want to be. And if the variation inflation factor is more than 2 or 3, simply you can say that there exists a multicollinearity amongst the independent variables. And how to go for it. Then the first thing is that how to solve this case. The question is, should I have to drop the variable? So if you find that there is a huge multicollinearity amongst the variable, then the easier way to drop that variable. But in research, if you drop a significant variable from your research or regression, then nothing left. So you want to know that what is this? What is the result of this change of that independent variable upon the dependent variable? And because of a multicollinearity exists, if you have to drop that, then it's your research has nothing left. So you have to deal with multicollinearity and how to resolve this case, that you also need to know. The first one is that you can go for a orthogonalization of the data. So if you can change the orthogonalization of the data set, then definitely this is one of the best method of reducing the multicollinearity. So you have to get the residual of the regression, that's the orthogonalization part of the data, and you'll get that collinearity doesn't exist if you take that residual or the after orthogonalization of the data sets. That's a simple one. The same data set we are going to use here, we want to check whether the exam scores will be the outcome of revision time, anxiety, and previous results, the 3 variables. Your independent variable is revision time, anxiety, and previous results, and your dependent variable is exam score. We are using the same syntax to go for the results, and the results come like this. So we can run it in SPSS, simple steps, we can use it. One thing I can show you prior to go to that if I go to this result, this data view table, we started with this 4. Now these are the results came, that's the residuals. So we standardize and unstandardized residuals. So, and standardized and unstandardized predicted values, this PRE stands for predicted values. RES stands for residuals. These two are for unstandardized. And if the Z is associated with prefix to it, it's basically the standardized predicted value and the standardized residual. Now you can go for plotting this. Actually, you can perform the Shapiro-Wilk test also to get it. Now I can run it for you. For you have to go for unstandardized coefficient. Now if you go to analyze, then go to descriptive statistics and explore. So these are the steps to go for diagnostic statistics for the residual. So if you go to analyze, then descriptive statistics and explore, there you have to put the dependent variable and your hours spent on revising your factor list. In statistics, nothing to do. In plots, you have to check for histogram and the normality plots with test. These two you have to go for. Keep remain unchecked all other options, nothing to do. Continue, bootstrap, nothing to do, just click away. So in statistics, we actually this descriptive 95% level is fitted, nothing to do. In plots, stem leaf we don't require, histogram and normality plots with test. That's two, you have to check it and then continue, and we have to go for okay. So we'll get the results of it. What happened? Something exam scores. So this is a histogram. It's processing. Normality QQ plots. So these are the results we are having. Let me check it if I have the results. Yeah, you can have these results also. Some problem occurs. Just let me run it once more. Analysis on residuals. Sorry, I have to run it on residuals. So analyze, descript statistics, explore. So your this unstandardized residual should be your dependent list. Unstandardized residual should be in your dependent list, and hours spent on revising that independent variable in your factor list. This is okay. Plots, I hope it's checked. Then I have to run okay. Now I'll get the results, I hope. Yep. So this is the histogram, something come like this. 2 points at the QQ plot. The data are very few. It will not able to give me the results. So data set is very few. That's why we are not getting the results. We can have this Kolmogorov and state the significance value somehow it's not coming. You can go for, that's why the something went wrong. Why this happens? So by this only you can have to check it. Just sorry for the something residual one. So you have to check for this data actually. This is the residual one, and you have to check for the normality of this. This Shapiro-Wilk can you can check for the scattered dot also from here. So whether it's a linear or not, unstandardized residuals. So you can do that also. So generally, what exactly that residual variable which is saved over here, you have to check it for it. Check that for actually. Now we're moving to the results. So if you can run the multivariate regression, just give me a moment. Now we have to run a multivariate regression. So we have to go to analyze, regression, linear, same thing. The exam score should be selected as dependent variable, and this all three actually you have to take it as an independent list. Statistics, you can go for a collinearity diagnostics. Plots, we don't require it. Save, yeah, you can go for standardized, unstandardized residuals and the mean, and then continue. Options, we have nothing to do. Bootstrapping we are not using, so we click on run and we get the results. So this is the first one, and we already interpreted the R square. That's a model that how the independent variable is going to explain the variability of the dependent variable. So here we are finding 86% of the variation of the dependent variable can be explained by the independent variable. Now there is a meaning of the adjusted R square, which is coming 0.83.4% or 8.834. Now generally we require try to increase the independent variable one by one. So here I just added two at a time. So it's better to use the independent variable one by one and try to check whether the R square value is increasing by adding one additional unit of independent variable. Now you can increase the number of independent variables up to that level. Say you have 10 independent variables. So you don't know whether it has an impact or not. This adjusted R square value actually helps you to understand whether that additional independent variable you are going to incorporate in your regression model will actually help you to understand whether this has any explanatory power or not. So if adding one additional independent variable in a regression model, the adjusted R square value is increased from its previous level, then only you should add the new independent variable, unless otherwise drop it. So you have to just go for a check uncheck and then you have to go for taking those independent variables only for which the adjusted R square values is going to increase. If by adding a one independent variable will not increase the adjusted R square value, it is advisable not to take it as an independent variable actually. Then the ANOVA results you also interpreted the same way. For the multivariate case, you have to analyze this, interpret this. Here the significance value is less than 0.05 at 5% level of significance. So we say that the model we fitted for a regression is a good fit model. You have to interpret the results in the coefficients. Here also unstandardized and standardized. If you are assuming we take the original scale data and the scales are same, then definitely we can use the unstandardized coefficients, and we can having the significance level of these three cases. For the alpha value is rejected, actually it's not statistically significant, but for the other three this first one, hours spent on revising, is significant and 5% level. This is at 10% level, and this is at actually also a 5% or 1% level of significance. So as the probability value is less than 0.05 in certain cases. So what we can say that the coefficients values are significant, and we have an interpretation of the coefficient value. Along with this correlation diagnostic, that's whether there exists any multi-collinearity amongst the variable, this VIF value is actually interpreted. So what we can say that if I take the search note that if the value is 3 less than 3, then there is no collinearity or multi-collinearity, then definitely here we can say that as the values are 2.28, 1.3 and 2.1 is less than 3, the variance inflation factor. So we say that the multi-collinearity amongst the independent variable doesn't persist or don't have it. So that's why the model is a good model. That's a simple one. That's a simple interpretation of the results. So this is more or less all of my presentations, and what exactly, if I can run once more, if I go to the data view also, if I have, we started with this 4, now we have this residuals actually. So if I just want to plot that residuals, let me check it once. If I can plot this residuals for you. Unstandardized dependent link this. See what if I can tell hours spent, the ITML level, my factor list. I go to plots, normality plots and histograms. If I don't want, continue. And if I go for OK, check. Missing this twice. It's not giving me the results. Yeah, something coming. So if I run it for one variable, I'll get that result. So this is the results actually, and if you check this significant value at different cases actually, generally for Shapiro-Wilk and Kolmogorov-Smirnov test for normality actually. So generally if the probability value is greater than 0.05, the assumption is the data or the is normal actually. So these two tests is basically the good test for check of normality in SPSS actually. And what Anandaraj Shah said told you that Jhargram statistics, that is basically not able to, we don't run it in SPSS. You have to use the views on Stata or R, you have to go for the Jhargram statistics. So here we can only have the Shapiro-Wilk and Kolmogorov-Smirnov test to check whether the data is not normal or normal. So if the probability value is greater than 0.05, we say that we are accepting the null hypothesis, the variable is actually a normal. So the residuals are coming normal, that's one assumption. And generally, if I plot the scatter diagram with this data set actually, so you have to go to the graphs, and if I go to the scattered dot actually, the simple scatter, if I want to plot it, I put the y-axis, the unstandardized residual, and in x-axis, if any one if independent variable we put, and if I just try to get the scatter. So generally, what exactly we can also fit a linear line over here. So to do that, you have to go to elements and fit a total line. So the total line is fitted, and exactly to check that whether the homoscedasticity exists or not, and what exactly we say that the more or less the variables are moving at a constant tandem along the mean line basically. So here we can say in a simple way, the interpretation is the variance or the data points are actually scattered, so the homoscedasticity is actually lies over here, don't lies over here. So the variance is not constant, or variance is varies. So if the variance is varies, then definitely it's, if it's not constant, then homoscedasticity is there. So that's a basic problem with this data set, and that's for the cross-sectional data. It's very difficult to get a homoscedastic data. So with this note, I hope I don't remain much of time left. So this is all my submission in front of you about the regression, bivariate and multivariate one. And if you have any questions, you can simply ask, or else. So thank you to all of you.
Sir, I have a question.
Yeah, sure, please.
Sir, one thing I saw that bootstrap, when it is used, sir?
See, bootstrap is basically to get the confidence interval level right now. Generally, we switch in a software from confidence interval level to actually what I can say, confidence interval level to p-values. Now, while analyzing in different good research paper, it has been found that accepting and rejecting with p-values is actually giving you not a good results. So again, we have to go for the confidence interval calculation in exact level, and this bootstrapping is one of the method by which you can also calculate the confidence interval level. Actually, we're using that for the this ACM models basically.
Okay. And sir, what is orthogonalization means? How it is used?
See what I can give you some sort of result, something in a stock market. Actually, if you say that you can take different variables, say market, you are regressing a stock return on market return or some variable. Say if my variable, independent variable is a forex and so Sensex, and you want to regress it for the one particular stock, then definitely you know that this forex have an impact on market, as well as the market also impact on a forex. So there is a causal relationship exists between and there is a high level of multicollinearity exists between two independent variable, but I cannot drop any one of these two. Now then basically I have to run a regression on this. Definitely stock market taken is a dependent variable and forex market taken is an independent variable, assuming a unidirectional causality. If I regress it, and the residuals what I left with, actually that residual value you have to take into consideration in a new model fit. So what exactly, instead of a market, then definitely you use the residual value of the market. So your next equation will be stock return is equals to alpha plus residual of market plus forex. So we are nullifying the impact of forex market into a stock market. The process by which we are changing it, the scale basically is called the orthogonalization.
Thank you, sir.
Any other question if you have any?
I hope my camera is probably not working. Some sort of problem is there.
No, I think
Is it
your
working?
your screen sharing is still on, I hope.
Okay, that's why. Yeah, I just I don't
Yeah,
know
now
whether.
it's okay. Now it's okay. Okay. Okay.
Am I visible to all of you? I don't think.
No, you are not visible.
Yeah, my camera is not working. That's I'm telling. Okay, thank you.
Okay, Lopamudra, please.
Yes, sir. Thank you, sir. Thank you for such a wonderful presentation. You have lucidly explained all the terms and terminologies related to regression, and I hope everyone present here has learned a lot today. Thank you so much for this informative and enriching session. Now we shall move on to our next technical session. Our resource person is Dr. Bidut Das. Is he present? Abhijit sir, is he present?
No, not yet, not yet. We have to wait a few minutes. I
Okay,
mean, 2 or 3 minutes. Then we
okay,
can go for the next technical session. Okay.
okay,
For the
okay. We
timing,
are
I
waiting for
request
some.
all of you to wait. Okay. And thank you, Dr. Shomo Shah, for such a wonderful session in such a short period of time. Okay.
You know that regression cannot be performed in only 1 hour. Okay, then
Yeah, that's true. That's
if
true.
I can add value at least 1% to the researchers, definitely it will be of a great.
Okay. Okay. Thank you.
Thank you.
Thank you very much. Just wait. I think Dr. Professor Bidut Dash will join in 1 or 2 minutes, and then we are going to start our next technical session. Please be with us.
Hello,
Dr.
I'm
Professor,
present here.
are you
I'm
there?
logging with Rishi Bhargav Das email ID.
Okay. So you are here. Okay. So we are starting. We are starting this session in 1 minute. Okay.
Okay.
Okay, sir.
Okay. Lobamudra,
Yes, sir.
you start introducing, sir. So
Okay,
by
sir.
that time, I think 1 minute will be
Okay, sir.
elapsed.
I would now like to introduce our next resource person before everyone, Dr. Bidut Das. He is an assistant professor in the Department of Statistics, Nowgong College, Autonomous Assam. He has done his graduation from the Cotton College, Guwahati. He secured first class second position. Then he has done his PG, postgraduate from Guwahati University, where he secured first class and second position. Then he has secured UGC CSIR. He has passed qualified UGC CSIR NET GRF. He has a specialization in multivariate probability distribution and queuing theory. He has worked as a RP programming reviewer in two Scopus and Web of Science journals and many other international journals. He has 5 publications in Scopus and ISSN journals. So I would like to request sir to take over the session now. Welcome, sir.
Thank you very much. Good evening, everyone. Am I audible?
Yes, sir, you're audible.
Now I'm starting data analysis using R software. So R is not is a simple software, but it's a fast one. No, history of R. The S language includes both R and S plus. R can be regarded as an implementation of the S language, which was developed at Bell Laboratories by Rick Becker, John Chambers, and Alan Wilkes. R was initially written by Robert Gentleman and Rose Ihaka of the Statistics Department, the University of Auckland. And since mid 1997, there has been a core group with right access to the R source. At present, it is maintained by a core group. Now, it runs on a variety of platforms, including Windows, Unix, and Mac operating systems. So, R is an outstanding statistical package, and it is free of cost, and one can download it from www.rproject.org. Introduction to R. R is used for statistical computing and graphics. Then it is used to store, manage, and manipulate data. It is also used to create graphical displays of data using different graphical system. It is also used to analyze data using standard statistical procedure and to perform simulations. So our overview. Hello. You can enter commands on at a time at the command prompt, that is greater than symbol, or run a set of commands from a source file. There is a wide variety of data types, including vectors, numerical, character, logical, matrices, data frames, and list. So one can quit R by the command greater than symbol Q. So most functionality is provided through built-in and user-created functions, and all data objects are kept in memory during an interactive session. Basic functions are available by default. Other functions are contained in packages that can be attached to a current session. Vectors. R has many types of data structures. Vector is one of the more important data structure in R. All the elements of a vector must have same mode, that is data type. So there are there are so many data types: numerical, character, logical. So one might have a vector of all numeric values, all character values, or all logical values, but not a mixture of data types. That means one cannot mix the logical values or character values or numeric values at a time. If a vector created with mixed mode, the individual elements are all forced to a single mode, such as character or numeric. So single numbers, R represents single numbers as scalars, do not exist as scalars in R actually. So scalars are presented in R as a vector with one element. So we have not any scalars in R. We have a vector with one element in R in lieu of scalars. So for R coding, vectors of length 1, we write this say x so 5. Then we initiated y as is a vector 1 with 3 elements combining values into y, and z is a vector with 4 elements. Now x plus y is x plus y. So R will take 5 plus 7, then 5 plus 3, then 5 plus 5. Similarly, if we take this C555 plus y, so that will give us 12. That means the shorter vector is recycled 3 times here. So x is a shorter vector, so it is recycled in 3 times. Similarly, when we add y with z, y is a vector of length 3 and x is a vector of length 4. So adding y and z, the vector 7 will appear twice. That means we have the vector 7, 3, 5, then again 7. So y plus z give us 7 plus 2, 9, then 3 plus 4, 7, then 5 plus 6, 11, and again 7 plus 8, 15. So we get 9, 7, 11, and 15. Similarly, if we write cy7 plus z, then it will give us 9, 7, 11, 15. So R normally shorter vectors is recycled in R. Now there are some logical values in R. Logical operators are used in R. So in general, our logical values are not enclosed in quotes. A true is stored as a 1 and a false as a 0. The logical operators that are used in greater than symbol, it's a greater than symbol, then less than, then this is less than and equal to, this one is greater than and equal to, this one is exact equality, and this one is vector intersection, vector union, this one is vector intersection, then vector equal to, then vector union, then scalar intersection, then scalar union. And this one is vector union, this one is vector intersection, and this one is vector union. But this is also a scalar intersection, and this is a scalar union. Then R code log back x less than z, that is logical vector. Logical vector, if we compare x and z, just you see in here x and z, so these two are x and z. So here if you compare x less than z, then 5 is less than 2 and 5 is less than 4, 5 is less than 6, and 5 is less than 8. Now 5 is not less than 2, so it is a false one. 5 is not less than 4, then it is a false one. 5 is less than 6, so it is a true one, and 5 is less than 8, then it is a true one. So for log back x less than z, we have log back 5 less than 2, 5 less than 4, 5 less than 6, 5 less than 8. We get false, false, true, true. So type of log vector determine how log vector is stored internally, and it is logical. Vector intersection and union in R code. If x is false, true, false, and y is false, true, true, then x and y, that is Boolean x intersection with y, we get false intersect. If we intersect false, false, then it is false, and true, true, it is true, and false, true, it is false. Similarly, if x union y, so if you unite is x with y, then false, false is false, and true, true is true, and false, true is also true. Now, if x is equality, then x is equal to y, then true, true, false. X is equal to y, so false, false means true, and true, true is also true, and true, false is false. Similarly, for Boolean inequality, then false, false is false, and true, true is false, and false, true is true. Similarly, if x, y, n, and y only looks at first element of each vector, that is this intersection of scalar quantity, and it gives us false. For false, false, intersection of false, false is equals to false. Similarly, union of x, y, it is also give us the first elements of each vector, union of first elements of each vector, and it is also false, false of union is false. Elements other than the first can be compared by specifying the index of the desired element in square brackets. For example, to compare the third element of y with the second element of x with the scalar intersection, one would use y3 and then x2. That is to compare third element of y with second element of 2 x. So third element y is true and second element x is true. So intersection of these two is true. There are some naming questions in R. Not to use names of function as C, capital C, small c, Q, small t, capital T, mean, median, and so on, because these are the functions of R. So one cannot use these functions as a for naming. So since doing so will change the meaning of said function in the current session and may result in unexpected consequences if any code calls function that has been overwritten. The object names cannot contain string symbols like exclamation or plus or minus or deadline. These are not used. A dot and an underscore are allowed. Also a name starting with a dot. Object names can contain a name number but cannot start with a number. So object names can contain a number but it cannot be start with a number. Similarly, R is case sensitive. So capital X and small x are not same, they are different. Similarly, if we write temp and temp, these are also different. So we cannot write temp and the next line we write is like TM capital P. These are different values and these meanings of these two variables are different. There are some reserved words in R. There are some reserved words in R that should not be used in object names, which are else, repeat, while, function, for, in, next, break, true, false, then NaN, then NA integer, NA real, NA complex, and NA character. So these are reserved words. One cannot use these words for naming objects in R programming. Now, vector indexing. Indices for R vectors start at 1. Individual in C or C++ programming, indices for C or C+ programming vectors are start at 0, but here in R programming it is start at 1. So individual elements of a vector are assessed with third brackets. Similarly, R uses NA to represent missing values. So if there is a missing value, R will show us NA. And NaN to represent not a number. So if we divide 0 by 0, then it will give us NaN. INF to represent very large number and minus INF to represent very small numbers. So R has a few built-in constants. So letters for capital letters, the 26 uppercase letters of the Roman alphabet, and letters, that is small letters, the 26 lowercase letters of the Roman alphabet. Pi, the ratio of the circumference of a circle to its diameter. So these are vector indexing in R. For R code NB, this is a vector. It takes the values -4, 0, 2, 4, 6. It's a numeric vector because these are numeric number. So NB by NB, that means we hear NB by NB, so -4 by -4, that is given, that will give us 1, and 0 by 0 is not a number, so here it is NaN. Then 2 by 2 is 1, then 4 by 4 is 1, and 6 by 6 is 1. Because we divide NB, we initiated NB as this, and NB by NB is, that means -4 by -4 is equals to 1, and 0 by 0 is not a number, so it is given as NaN, and 2 by 2 is 1, and 4 by 4 is 1, and 6 by 6 is 1. Then SQRT and B cannot take square root of -4. We cannot take square root of -4, so it is become as NaN. So whenever we get, there is not a possible number, that is not, I mean to say, that is not possible, then it will become as NaN. And now next our, if we square root of 0 is 0, and square root of 2 is this, and square root of 4 is this, and square root of 6 is this. So it will become as warning message in square root NB nonce produced. So I will show this message also. Now NB to the power 999. So it's a very small and large number use INF and minus INF and plus INF, not plus INF, it is INF. So minus INF is used for very small number, and for large number we use INF. Now if we -4 to the power 9999, it will give us negative, that is a small number, so it is become as minus INF. Now 0 to the power 999 is equals to 0, and 4 to the power 99 is a very large number, so it is INF. Then 4 to the power 999 tetra 9, it's also a very large number, so it is INF. Then 6 to the power 9999 is also a very large number, so it is INF. Elements can be omitted from a vector by using a vector of negative indices inside the square brackets. Positive indices extract the index values of the vector. For example, nv minus 1 omit first element of nv. That is our minus 4. Our minus 4 is omitted here. So we get 0246. Now nvc13, we extract first and third element of the nv. So our first element is minus 4 and third element is 2. So we get minus 4 and 2. Now, generating vector sequences and repeating vector constants. This is a colon operator, and the sequence this of functions can be used to generate useful sequences. The function REP, that is repeated, allows the user to create vectors with repeated constants stored in a vector. For example, suppose we write 24:20. That means we have written the numbers 24 to 20. So 24, 23, 22, 21, 20 will occur. Again, if you write letters 20 to 24 to 20, so 24 through 20 lowercase letters will come. That we have written here lowercase letters. That was X, W, P, U, T. These are the 24. Then 23rd, 22nd, 21st, and 20th letters, lowercase letters come here. And sequence from, suppose we write a sequence from equal to 5 to 25 by 5. So it is increased by 5, starting from 5 and end into up to 25. So it is 5, 10, 15, 20, 25. And sequence from 5 by 5, length dot out 5. It's also 5, 10, 15, 20 to 25. Because length out is 5 and increase by 5 and start from 5. So we have 5, 10, 15, 20, 25. The sequence from 23 to 22, length out is 5. So we have to divide this 1 into 5 part. So starting from 23, next will be 22.75, then 22.50, then 22.25, then 22. Sorry. And then REP x equals to 5, 10 times 10. That means values of x equals to 5 will be repeated 10 times. So we get 5, 5, 5, 5 of 10 times. Then REP x equals to C true false times 4. So our true false will occur 4 times. That is true false, true false, true false, true false. Right. Filtering vectors. Filtering allows the user to extract elements of a vector that satisfies certain condition. For example, FEP repeat x equals to 3 is to 1 times equals to 1 is to 3. So FEB, then it will give us 3, 2, 2, 1, 1, 1, 3 times. That means here we have numbers 3 to 1, but our 3 will occurs 1 times, and here is number 1 to 3. So 3 is occurs 1 times, 2 is occurs 2 times, and 1 is occurs 3 times. So we get 3, 2, 2, 1, 1, 1. Then FEB star FEB, that star is also a similar product function like others programming language. It is also used as a product function, and FEB product FEB, that will give us 9, 4, 4, 1 into 1 is 1, 1 into 1 is that's 1, 1. And FEB star FEB greater than 3, that means 9 is greater than 3, so it is true. 4 is greater than 3, it is true. 4 is greater than 3, it is true. But 1 is not greater than 3, it is less than 3. Therefore, 1 is greater than 3 means it is false, and 1 is greater than 3, it is false, and 1 is greater than 3, it is false. So true, 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 then false, false, false. Similarly, FEB, if we construct it like this, third bracket FEB, star FEB greater than 3, so it will give us 3, 2, 2. That means we will get only length of 3, 2, 2. That means our an equivalent approach using subset. Subset x equals to FEB, subset FEB star FEB greater than 3 is also 3, 2, 2. Instead of the actual values, we may want the indices where these values occur, which FEB star FEB greater than 3 is 1, 2, 3. Our data structure used here includes vector, arrays, matrices, factors, list, and data frames. Arrays and matrices. Arrays are multidimensional arrangement of elements. A very common example of an array is a matrix, which is two-dimensional array. R code for array and matrices. Suppose we have taken A1 as the array data from 1 to 20, the 1 is to 20, dimension is C342. So A1 we get like this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 2, it is 13, 16, 19, 22, 14, 17, 20, 23, 15, 18, 21, 24. Is array A1 true? Is matrix A1 false? Array A1 is true, but matrix A1 is false because it's not a matrix, it is a array. Because we have dimension 3, 4, 2. Now, array dimension A1 is 3, 4, 2. Now, a 4 by 6 matrix is constructed and stored in the object M1. M1 is taken as an array, data 1 is to 24, dimension C, 4, 6. So M1, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like this, and up to 24. So here we have 4 rows and 6 columns. So first one is rows, second one is columns. Now, is array M1 true? M1 is an array. Every array is a matrix. Sorry, every matrix is an array. Then is matrix M1 is true. Then class M1 matrix. Then dimension M1 is 4 and 6. For M2 matrix, data is 1 is to 24. N row equals to 4 by row true. Now row measure order M2, we have row measure order, so we get 1, 2, 3, 4, 5, 6, then 7, 8, 9, 10, 11, 12, then like this. And if you write this M3 matrix data this N equals 6 by row false, column measure orders, then we get 1, 5, 9, 3, 13, 17, 21, like this, 2, 6, 10, 14, 18, 22, 3, 7, 11, 15, 19, 23, then 4, 8, 12, 16, 20, 24. Suppose a matrix is given is like this: A equals to 257, then 4, 3, 1, 9, 6, 8. So can be arranged in our code as written below. We data see this, we write this C 2574 2574. That is, we have written row wise 2574 31967 968. So A dot data is matrix data. Our small data, this is capital D is equals to our small d data. So n row equals to 3 and by row is 2. Therefore, A data is like this: 257, 431, and 968. Then vector and matrix operation. Consider a system of equations. Suppose we have a equation, we have to solve for x, y, and z, and the equation is 3x plus 2y plus z equals to 10, and 2x minus 3y plus z equals to minus 1, x plus y plus z equals to 6. The system can be represented with the matrices and vectors as ax equals to b, where a is 3, 2, 1, 2 minus 3, 1, and 1, 1, 1. And our x is xyz, and our b is 10 minus 1, 6. So we can solve it easily. So A is a matrix. See this 3, 2, 1, 2 minus 3, 1, and 1, 1, 1. By row it is true, and row equals to 3. So A, our matrix is like this: 3, 2, this. And B matrix, this is our 10 minus 1, 6. This is our B's values of the solution. So by row equals to 2 and n row equals to 3. That the B, so B will give us 10 minus 1, 6. Now we can solve it simply. We write solve A comma B. Under first bracket we write solve A comma B, and we initiated the values x to this, and so x if the values of x is equals to 1, 2, 3, so that means x value of x, we denote this x y z by the variable x. So our value of x is 1 and value of y is 2 and value of z is 3. Then R factors are there. A factor is a vector with additional information indicating the distinct values or labels of the vector. Many statistical problems use categorical variables to classify subjects or to subdivide the data. When using R, one should store categorical data in factors. To create a factor from a vector, we use the function factor function like this. This is v and C 2102 and FV factor V FV, then it will give us 2102 and levels 012. And FV factor V levels 0 to 2, level C easy, difficult, impossible. So our impossible will become fast, then difficult, then easy, then impossible. And levels are easy, difficult, and impossible because he has 2102. So our 2 is this, 0 is this, 1 is this. So we get impossible, difficult, easy, impossible. Again, our levels are 0, 1, 2. So we get easy, this is 0, and difficult is 1, and impossible is 2. Now list. A list is an object whose elements can be of different modes for a character, numeric, logical, etc. Lists are used to unite related data that have different models. Since many R functions return results using list, it is important to know how to extract information from a list. So it will denote as TU1. List first dot name equals to Bob, then last dot name is Smith, major statistics, then semester dot hours equals to 18 grades, say A, B plus, A minus, C plus, B, B minus, names is to 1, and we grades C analysis, experimental design, English, Bengali, regression, programming, and is to 1, first name Bob, and last name is Smith, major statistics, semester hours, it is become as it will give us analysis analysis as grade A, experimental design grade B plus, English A minus, Bengali C plus, regression B, and programming minus B. And names is 2 is first name, last name, major, semester hours, grades. Now is to 2 list Bob Smith statistics 18 C A B plus A minus C. It will becomes 2 Bob, then Smith, then sticks 18 this A plus B plus A minus C plus B minus B. Data frames. A data frame is similar to a matrix in the sense that it is a rectangular structure used to store information. So data frame is a rectangle similar to a matrix, and it is a rectangular structure, and it is used some information used to store some information. It is different in that all elements of a matrix must be of the same mode, numeric character, etc. But this restriction does not apply to data frames. The function data.frame can be used to create a data frame by using equal length vectors as the first arguments of the data frame function. For example, suppose we write NB C1368, it is numeric vector, then CBCADFP character vector, and LBC true false false true is a logical vector. So we denote DF1 as data frame NBCBLV. So DF1 will give us this like this. NB is 1368, CV is A, D, F, P, and LB is true, false, true, false, false, true. Then STRDV give us data frame for observation of 3 variables, and NV nums is 1368, and CV factor W4 levels A, D, F, P 1, 2, 3, 4, and logical it is true, false, false, true. Similarly, DF2 data frame NV CVLV row dot names is equals to C, Joe, Bob, Jill, Sam, strings as factors is equals to false. So DF2 will give us NV CVLV as like this 1368 ADFP and 2 false false true. Steer DF2 data frame 4 observation and 3 variables, and its num is 13, this numeric 1368, and characters ADFP, and logical is true, false, false, true. And we can use RM is a remove function, and it removes the variables from the current environment. Once if one use RM, then it will remove the variables from the current environment. Reading and saving data in R. So R has the ability to read data from external files stored in several formats. to read data in formats other than ASCII, the package foreign can be used. So you won't have to use foreign package, and this package is able to read formats from other statistical programs such as Minitab, S+, SAS, SPSS, Stata, and SysStat. For more information on reading data from other statistical programs, relational databases, and binary files, please reference the R Data Import Export Manual available online and accessible from R HTML help menu or the help component of RStudio. Using read.table and download.file and scanner. These are the functions of R. The function read.tables reads a file in table format, a rectangular dataset, and creates a data frame from that file. The function download.file downloads the file from the internet and allows the user to specify where they want the downloaded file saved by providing a character string specifying the path, including the name of the downloaded file to be saved to the dest file argument, that is destination file. The function scan works well for entering a small amount of data by either typing in the console or by using a combination of copying and pasting procedures when the data can be highlighted and copied. Reading Excel files, so it can import files from Excel Excel sheets. The Excel SX package, which must be installed, gives programmatic control of Excel files using R. The function read.excelSX can be used to read an Excel workbook stored as a .excelSX file. When the workbook consists of multiple worksheets, the argument sheet name is used to specify the desired worksheet. Function sort merge. The sort function can be used to sort a single variable in either increasing or decreasing order. To sort a data frame in R, use the order function. By default, sorting is ascending depend the sorting variable by a minus sign to indicate descending order. Here is an example. So this is 111 333 3 2 2 2 2, then Y 323 626 1044, then Z 74 742964531. So DF, we initiated DF as data frame XYZ, and RM remove the XYZ, remove XYZ from workspace, and TDF is transpose of DF. So we get 111333 222 323 1044, then 742964531 with the data DF T transpose disorder will give us 23 23198 7564, then X 111 222 333, Y 233 444 10266, Z 427 135649. Now that X is ordered first as 1 to 3, then where X values are tied, Y values determined the next ordering. Under the 1 for X and Y's values appear in 2 3 order. Under the 2 for XY's values appear in 4 and 10 order. Under the 3 for XY's values appear in 2 6 order, where Y's values are tied. The values for Z determines the final ordering. Thus, the XYZ triple 1 3 2 precedes 137, then 241 is before 243, and 364 comes before 369. Next, merging data frames. To merge two data frames, data sets horizontally use the merge function in most cases. You join two data frames by one or more common key variables, that is an inner join. Merge two data frames by ID, total merge data frames, data frame A and data frame B, there are two different types of data frame, by equals to ID. So merge two data frames by ID and country to merge data frames A, data frame B by C, ID, country. Some useful function: length, object, number of elements or components. Then str object, structure of an object. Then class object, class or type of an object. The names object, names. C object, object. Then combine objects into vector. C bind object object, which gives us combine objects as columns. R bind object object gives us combine objects as rows. Is list current objects. RM object delete an object, that is remove an object. New object edit object, edit copy and save a new object. Fix object is edit in place. So there are some arithmetic operators in R. The plus is a operators plus. Definitely is used at addition. Same as minus, it is subtraction. Then star multiplication, slash division. Then exponent or double star is exponentiation. Then x percentage y modulus x mod y, that is 5 modulus 2 is equals to 1. So if we divide 5 by 2, then we will get uh, remainder is 1. And x percentage y is integer division, that is 5 percentage slash percentage 2, it is give us 2, that is dividend is 2. Now numeric functions abs x gives us absolute value, then square root x is square root, ceiling x, ceiling 3.475 is 4, then floor x, floor 3.475 is 3. The ceiling is ceiling in the upper part and floor is this lower values taken as lower part. Trunk x is trunk 5.99 is 5, and round x digits and round 3.475 digits 2 is 3.48. Then signif, that is digits n, signif 3.475 digits to 2 is 3.5. Cos x, sin x, tan x, these are the trigonometric measures. Also a cos x, cos h and a cos h x, etc. And log s, natural logarithm, log 10x, common logarithm, and exp is e to the power x. There are some character functions. Suppose this is sub str x start equals to n1 and stop at n2. This say extract or replace substring in a character vector. X less is equals to abc s taken the values abcd, and substr x to 4 is bcd. Then substr x to 4 is 2222 is a 222 ef. Similarly, grep pattern x ignores dot case equals to false, fixed equals to false. Search for pattern in x. If fixed equals to false, then pattern is a regular expression. If fixed equals to true, then pattern is a text string. Returns matching indices. grep cbac fixed true returns 2. Then sub pattern replacement, ignore case false and fixed false. These are find pattern in X and replace with replacement text. If fixed false, then pattern is a regular expression. If fixed equals to T, then pattern is a text string. So this hello there, returns hello there. Then str split, X split, and split the elements of character vector X at split. Then str split ABC returns 3 elements, vector A, B, C. Then paste this concatenate strings after using sep string to separate them. Paste this returns this x1, x2, x3. Paste x1 3 sep m returns xm1, xm2, and xm3. Paste today is date. Then two upper x uppercase, two lower x lowercase, and some probability distribution function. The following tables describe the function related to probability distribution. Yes, denom x function, denom x, normal density function. By default, m equals to 0, sd equals to 1. For normal distribution, mean equals to 0 and sd is 1. So it's the standard normal distribution actually. So plot the standard normal curve, and x pretty c minus 3 3 comma 30, y denom x, plot xy type, L XLB normal deviate, YLB density, y axis I. P norm is cumulative normal probability for Q. Area under the normal curve to the right of Q from a P norm is 1.96 is 0.975. Then Q norm P is normal quantile value at the P percentile of normal distribution. Q norm zero point 0.9 is 1.28 and is 90th percentiles. Then R norms n m equals to 0 s d equals to 1 and random normal deviate with mean m and standard deviation sd. So 50 random normal variates with mean 50 SD 10. Then X will write this and R m norm is 50 m equals to 50 and SD equals to 10. Then D binom, it is binomial distribution and it is X size probability. So X the binomial distribution where size is the sample size and probability is the probability of a heads, that is our PI. And then we get p binom for q size probe, p size probe and n size probe. So probability of 0 to 5 heads of fair coin out of 10 flips. D binom is 0 to 5, 10 to 0.5. Then probability of 5 or less heads of fair coin out of 10 flips. P binom is 5, 10, 0.5. Similarly, d poise is x lambda. It's a Poisson distribution. If we use this function for a Poisson distribution, so Poisson distribution with m s d lambda, and probability of 0, 1, or 2 events with lambda equals to 4. D poise is 0 to 2 to 4. Then probability of at least 3 events with lambda equals to 4. 1 minus p poise to 4. Then it is uniform distribution and x mean equals to 0, max equals to 1 for uniform distribution, range is 0 to 1. So uniform distribution follows the same pattern as the normal distribution above and 10 uniform random variables x, this is if 10. Now there are some other function mean extreme 0 then na.rm false. So mean of x, mean of object x. Trim means removing any missing values and 5% of highest and lowest score makes this mean x comma trim 0.05 na.rm equals to 2. Then SDX is standard deviation object x. Also look at variance x for variance and med x for median absolute deviation. So median x is median. Then quantile x props, quantiles where x is the numeric vector whose quantiles are desired and probability is a numeric vector with probabilities in 0 and 1. 13th and 84th percentiles of x, by for quantile xc 0.3, 13th means 0.3 and 84th means 0.84. So we write quantile xc is a vector and 0.3, 0.84. Range x is range, sum x is sum, the difference x and leg is equals to leg difference with leg indicating which leg to use. Then mean x is minimum, max x is maximum, scale x center equals to 2, scale equals to 2, the column center or standardized matrix. So some examples are there. So there's an example, the numerical grades achieved by 3 students on 4 exams during the course of a semester are recorded as given below. Compare means and medians of the students. Which students you characterize as overconfident? Which was a procrastinator? Which was consistent for the following data? So student stage score, test 1, test 2, test 3, test 4, and student 1 scored 73, 75, 74, 74, student 2, 95, 94, 12, 95, student 3, 66, 67, 63, 100. Now for R code we write student 1 C 73, 75, 74, 74, then student 2 C 95, 94, 12, 95, student 3 66, 67, 63, 100. So median student 1 is 74, median student 2 is 94.5. R will give us, if we write median student 1, then R will give us 74, and median student 2 R will give us 94.5, median student 3 R will give us 66.5. Now SM are bind student 1, student 2, student 3. So column names, that is call names SM, denoted by column call names SM, and it's a vector test 1, test 2, test 3, test 4. And when we write SM this, we'll get test 1, test 2, test 3, test 4. and student 1, student 2, student 3. That is test 1 is 73, 95, 66, test 2 75, 94, 67, test 3 is 74, 12, 63, test 4 74, 95, 100. Then means equals to apply Assam, comma 1, comma mean, that is mean of rows this, and medians apply this, Assam is median of rows. Then tot is C bind, Assam means medians, combined columns. So tot will give us student 73, 75, 74, 74, mean is 74, medians is this. And for student 2, 95, 94, 12, 95, that is mean is 74 and median is 94.5. For student 3, 66, 67, 63, 100, 74, 66.5. Here mean is 74 and median is 66.5. Now from above it is clear that these are very consistent. So student 1 is a consistent because his mean and medians are equal. So this one is consistent one. And student 2 is overconfident because his mean is 74 and median is 94.5. So he is overconfident. And student 3, his mean is 74 but his median is 66.5. So he is a procrastinator. And another example, for consider the problem of calculating the probability of obtaining 6 or more heads in 10 tosses of a weighted coin, where the probability of obtaining a head in any given trial is 0.33. So probability of getting head is probability of success is equals to 0.33, where we have only calculating the probability of obtaining 6 or more heads in 10 tosses. So we toss 10 times and we have to calculate for 6 or more heads. Now for our code, we write some d binom. For here it is a binomial distribution because this is follows binomial distribution. And here we use d binom 6 to 10, 6 is to 10 and 10 comma 0.33. So here 10 is our number of tosses and the 0.33 is the probability of success. That is, we have to calculate probability x scatter equals to 6 and this will our 0.07320046. It's, if you write 1 minus p binom 5, 10, 0.3, that is 1 minus probability x less. So then the x probability of x getter equals to 6 means 1 minus probability x less or equals to 5. So we can make it 1 minus p binom p 10, 0.33. That will also give us same result. And if you write p binom 5, 10, 0.33 lower equals to false, that means probability x getter equals to 6. So instead of writing some d binom 6 is to 10, 10 comma 0.33, we can write p binom 5, 10 comma 0.33 lower equals to false. Then this two will give same result. And similarly we can write 1 minus sum of d binom 5 is to 0, 10, 0.33, that is 1 minus probability x less equals to 5. So these are all same and we can use two types of functions in our programming. Now for if x follows normal distribution with mean 100 and SD 10, then the find probability of x lies between 90 and 115. So we can use our code p norm 115 110 minus p norm 90 110 because it is lies between 0 to 90 and then 0 to 15. So we can write 0 to 15 minus 0 to 90. So from 0 to 115, 0 to 115, we can calculate p norm 115, comma 100, 10 minus p norm 90, comma 100, comma 10. And it gives us 0.7745375. Other useful functions, there are so many functions, but we use sequence from 2 by. So we've already described it, generate a sequence, indices sequence. This 110 indices is C13579 because it increases by 2. So from starting 1, the next one is 3, the next one is 5, and the next, if we increase by 2, 7, next we increase by 9, and if we next increase by 2, that will be 11. But our limit is up to 10, so we have up to 9. Then repeat x 9 n times, that means x will appear n times. Now 1 is to 3, so 1 is to 3 2, that means 1 2 3 will repeat it 2 times. So 1 will repeat it 1, then 2 will repeat it 2, then 3 will repeat it, then again 1 will repeat it once, then 2 will repeat it, then 3 will repeat it 3. And cut x10, divide continuous variable in factor with n levels, y cut x5. Thank you. There are so many things in R, but I have not covered all of those things.
If anyone has any question, then they can ask, sir. I don't think anyone has any question. So I would like to thank sir for such a wonderful presentation considering the time constraint. Sir, whatever you have delivered today, I think it will be extremely beneficial to all research scholars, students, and everyone present today at this workshop. Thank you so much.
Thank you very much.
Okay, thank you, sir. Thank you actually to both of our resource persons who delivered lectures on two different aspects of data analysis today. And with this, we come to the end of today's sessions. And just to announce two or more things, like tomorrow's session will start from 6 p.m. Okay, so it will be 6 to 9 p.m. Course tomorrow. One first session 6 to 7, and next session would be 7 to 9. And so I request all of you to join tomorrow to this platform by 5:45 p.m. Second, the feedback form for both of these sessions today will be shared in your WhatsApp group. Please fill up them. And third one, please maintain your attendance throughout the, these particular sessions. It would be beneficial for your future research work as well. So with this, I hope both of the sessions that we have today will be very helpful. And we come to the end. And so wishing you a very good night. So thank you. Thank you very much.
Thank you so much.
Thank you. Thank you, sir.